This is Mrs. Johnson, and I'm going to talk to you a little bit today about simple machines and how they make work easier. So, we just got through talking about what work is and how work is moving something with a force over a distance in the same direction of the force. Pretty simple, straightforward thing. So, in order to make work easier, if we are having trouble moving something because either it requires too much force or you have to move it too far, then one way to make it easier to do that work is by using a simple machine. And you learned about simple machines when you were, I'm guessing, third grade. You learned there were 6 simple machines, and you probably played with them and memorized their names. So in the 8th grade, when we're talking about simple machines, what we're going to talk about is what is a good design for a simple machine, and how do you improve the design, and what happens when you use a simple machine to make work easier. And so that's what we're going to focus on today. As I go through and talk about each simple machine, I'd like you to fill out your simple machine design notes and just take notes as I talk through this and show you the pictures. And you're going to kind of draw some pictures of good designs of simple machines that we talk about and what they're used for and how they help us do work. So let's start with the pulley. This is a picture taken in India of a pulley that someone has in their home, because in India they don't have running waters in some places, and so if they want water in their house, they have to dig a well. And so this is a pulley called a fixed pulley. And the reason why it's called a fixed pulley is because the wheel is actually attached to the ceiling and it doesn't move. It turns, it rotates in place, but the wheel itself is fixed. It's in a stationary spot. And the reason why people used fixed pulleys like this is not because something is too heavy. The reason why people used fixed pulleys like this is to reach stuff they wouldn't normally be able to reach. And so if you put a fixed pulley here, you can reach really low places, or sometimes we put fixed pulleys on things like stage curtains because they're really big and you can't reach the top of the curtain to move it. Or we put fixed pulleys on flagpoles to reach the flag. Otherwise, we would have to shimmy up that pole to get the flag down. So that's really what fixed pulleys are used for. They are considered to have no mechanical advantage, or sometimes it's said that they have a mechanical advantage of 1 because they multiply your force times 1, which means if I want to lift something that's 50 pounds, if I use a fixed pulley, I'm going to have to pull with 50 pounds of force because I'm not going to be helped in that way with a fixed pulley. Okay? Other pulleys are used for other things. This right here on the left side, I think is a picture of Hong Kong. I'm not really sure, but it is a movable pulley. And the reason why it's considered a movable pulley is because the wheel itself is not in a fixed spot. The wheel is what moves along the rope instead of the other way. And that's called a movable pulley. Movable pulleys do have a mechanical advantage of 2, which means they decrease the force that you need to have by half. They multiply whatever force by 2 that you pull with. So if I pull up on a movable pulley and I have something on a movable pulley, I'm only going to need to use half the force to move that. Now, I would say in real life, most times when you're using a pulley because you can't lift something because it's too heavy, you're going to have a pulley system. Sometimes pulley systems are called block and tackles, and block and tackles are these things right here. They are multiple pulleys. So you have a bunch of fixed pulleys and then you have a bunch of movable pulleys, and they work together to increase your mechanical advantage. And mechanical advantage just means how much is your force multiplied by. So all of the weight that something is pulled up with a pulley is distributed along all of those strings. So however many strings you have that distributes the weight on, that is your mechanical advantage. That's how many times that thing is going to multiply your force. So if you look at the pulleys, the pulley in the middle on this picture, I count 6 strings. That means that I can lift something that's 6 times heavier than the force I'm pulling with. So if I am pulling with 50 newtons of force, I can lift a 600 newton object, 6 times that. And they use pulleys like this in machine shops sometimes. If you have a mechanic who doesn't have like a hydraulic lift, sometimes they'll use these to lift motors out of vehicles. You'll see block and tackles like this on big ships, like crab boats and fishing boats, to lift in the nets or the pots, the crab pots, because they get really, really heavy when they're full. And so that the guys can lift it, they use these block and tackle systems. The thing about pulleys, though, the more times that a machine, any machine, multiplies your effort force, if the force goes down that you have to pull with, then the distance you have to pull goes up. And that's called the force-distance trade-off. Because work is force times distance, right? So simple machines don't increase the amount of work done. All they do is they make it easier by playing with the force or the distance over which it's applied. So if you want to lift something heavy, you might have a mechanical advantage of 6 to where you only have to use a sixth of the force, but you have to pull that string 6 times farther in order to get it to the same height. And that is called the force-distance trade-off. Now, sometimes machines don't work as well as they should, because why would a pulley system not work as well as it should? Because sometimes when you're using a pulley, it's supposed to have a mechanical advantage of 6, but it doesn't. It might only have a mechanical advantage of 5 or 4. What causes that is friction. Friction works against the motion of things, right? So if you have a lot of friction in your wheels between the rope and the pulley wheel itself, then you're going to decrease the efficiency of the machine, and so it's not going to work as well as it could. And so that's why you have to take care of your simple machines. You have to oil those, put lubricants and put oil on those wheels to make them be able to move easier. The next thing is an inclined plane. An inclined plane is used to make work easier as well. And so the longer your inclined plane is, the less force you're going to have to use to move up the inclined plane. But if the inclined plane is longer, you're going to have to move it a lot farther, which is also part of that force-distance trade-off. Inclined planes are made for going up and lifting things easier, which is why we use them when we're moving trucks or in warehouses, when you're trying to lift heavy objects. Sometimes inclined planes are used for people with wheelchairs, or I know my dad has trouble walking up steep stairs, and so he always uses the inclined planes. And if you notice, though, those inclined planes, if you add up all that distance you're walking, it's way farther. So you might have to use a third of the force to go up it because it's not as hard, but you'll have to go 3 times farther to get there. And again, that shows you that force-distance trade-off that simple machines use. How do you think that this ramp helped this guy do work? Okay, what could reduce the efficiency of a ramp? I would say friction. Now, if you're pushing something up a ramp, friction would work against the motion going up it. But if you think about it, if you have not enough friction, it might reduce the efficiency because you're slipping and not being able to move up the ramp like you should. So friction really affects the efficiency of machines. Okay, this is a really cool picture I found. This is Reading train station. If you've ever played Monopoly, there's the Reading Railroad. A lot of people call it the Reading Railroad, but I learned on NPR one day that that's actually called Reading, Pennsylvania, that station is at, and it's a real place. And this is a car exit. And so if you wrap an inclined plane in a circle, what you have is a screw. And screws are used for a couple of different reasons. One reason screws are used is to fasten things together, because if you have a screw instead of a nail, if you remember talking about friction, friction is caused by those little hills and valleys sticking together. And so the more those hills and valleys can touch each other, the more friction there's going to be. And so if you take a nail and you wrap an inclined plane around it, you just added a whole lot of surface area for friction to occur. And so that's why screws hold things together better than nails. Now, if you were to take the inclined plane that's wrapped around a screw and like magically undo it and measure the length of the inclined plane, the longer the inclined plane is, well, the closer those threads are together. And so if you have a longer inclined plane, going back to inclined planes, the longer the inclined plane, the less force needed, right? Same thing applies here. What you have is the really long inclined plane. So if you have a screw where the threads are really close together, you have a really long inclined plane, it's going to be easier to screw that into the whatever you're holding together. So if I'm screwing something into a board, if I have a screw where the things are really close together, it's going to be a lot easier to turn that screw into that board. However, I'm going to have to turn it a lot more times to get it into the board. So that's the mechanical advantage of a screw. The closer those threads are together, the easier it is to turn it. But the more times I'm going to have to twist that screwdriver to get it into the wood. There's the force distance trade-off again. So we said they're used to hold things together. They're used to fasten things, and that's what screws are used for. Wheels and axles are like large levers. And the reason why we use wheels on axles is to increase mechanical advantage, because it's hard to turn an axle without a wheel on it. It requires a lot of force. And so if you've ever tried to open a door that doesn't have a knob on it, it requires a whole lot of force to turn that axle. But if I stick a knob on it, what I've done is multiplied my force at the expense of distance. So I have to turn it farther around, but I don't have to use as much force to turn it, which is that force distance trade-off again. Now, let's say I don't need to multiply the force. Let's say I've got a motor doing my work for me and I don't really care that it's going to have to work a little harder. Well, then you can also use a wheel and axle to increase the distance over which the force is applied. So if I turn an axle one time and it's got a small wheel on it, a car will go a certain distance. But if I put a bigger wheel on that same axle and I turn it one time around, well, the distance around a big wheel is a lot farther. And so you can go farther with each turn the bigger the wheel is. And so wheels and axles can be used to increase the force if you need it to open something, or, for example, even like turning a ship. You have a great big wheel on a ship because it's hard to turn, and so that increases the mechanical advantage. Or it could be used like on a vehicle to increase the distance over which it's applied. Okay? The last one is a lever. That's the last one I'm going to talk about, and a lever is used to lift things. And a lever has three parts. It has the part where you put in your effort force. For example, the effort arm of this lever would be from the top of it to where I'm holding the handle. You have the fulcrum, which is the pivot point, if you'll remember that. And then you have the resistance arm, which is also called the load side, and that's what you're trying to lift. And so the bigger the difference in the lengths of the side that you're pulling on and the side that you're lifting on will give you a greater mechanical advantage. So if I want to lift something with a lever, the farther you lift, the farther your effort is from the fulcrum compared to your load to the fulcrum, the easier it is to use and the less force you're going to need. But again, in order to lift that load, you're going to have to lift a lot farther to get the load to move a little bit. And that's the force distance trade-off of a lever. And I forgot about the wedge. I can't forget about the wedge. The wedge is something that concentrates effort force, and it's used for splitting or cutting usually. And the point of a wedge is you take the effort that's applied over the top of the wedge, and then you concentrate that effort force over a very tiny distance. And what that does is it it concentrates that force to where it can split things easier. And so the bigger difference between the side that you put in the side that you hit and the side that you cut with, the greater the mechanical advantage, which is why you sharpen knives. A knife is a wedge, right? So when you sharpen one end of the knife, you're making a bigger difference between the side you're pushing with and the side that you're cutting with. Forks are also wedges. High heels are also wedges. This is funny. Back in the 80s when spiked high heels were kind of in, this is not really a spiked high heel. They were really, really tiny on the bottom. There were a lot of government buildings who were having trouble with their floors because all of their floors were getting like these holes in them, these tiny little holes. And they figured out that it was all the ladies' shoes that were wearing high heels at the courthouse. They were putting holes in all of their floors because they were basically using them as wedges. Any questions? Okay, let's do some practice. In your notebook, see if you can answer these questions. If I want to make this lever easier to lift that load, would I move the fulcrum toward the load or away from it? The answer is I would move the fulcrum toward the load because that would make the length of the lever that I'm using greater than the length from the fulcrum to the load. And that would increase the mechanical advantage. What if I wasn't strong enough to turn this wheel? What could I do? Well, I could make the wheel bigger, or I could make the axle smaller. All right, that's the end of my presentation. Get ready to do a checkpoint for understanding.